Today we're going to look at how to cut a pinion, or if you prefer, it could also be called a spur gear or a straight tooth gear. Now, before we even consider looking at how to cut a straight tooth gear, we're going to have to look at one of these indexing heads or dividing heads. Since we're cutting a gear, we're going to want to rotate the part very accurately for each tooth, and this apparatus will permit us to do just that. So let's take a closer look at it. So, the three main components of this apparatus are the footstock. The footstock is used to support. It's a bit like the tailstock on a lathe, but with one big difference, and that is that this center is a dead center. It's not made to rotate. It's just there to support, and you can't mount in this machine a drill chuck or other apparatus. It's really not for that. It's just to support a part between centers. It's bolted to the table and has to be adjusted to line up with the dividing head. Closer to me we have the center rest, which is used to support a part. Since milling operations, more specifically climb milling operations, have a lot of downward thrust. And we want, when we have a part mounted between centers that is a little bit long, to support it so that it won't flex downwards or vibrate. And closer to me we have the dividing head itself. It's a complex assembly, so let's take a few seconds and look at it in greater detail. So let's take a look at the different components of this part of the dividing head. The head itself, this portion here, that looks a lot like a headstock. And let's get rid of the center rest. We won't really need it for the gear that we're going to be cutting, because the fixture that we're going to use is quite short and not very flexible. So let's start with this live center. It's the center that turns with the spindle of this dividing head, and it plays a support role when holding parts between centers. Now, this center can be replaced by a chuck, a 3-jaw or a 4-jaw chuck. Since the dividing head can be inclined, we won't always hold parts between centers. But when I do hold a part between centers, well, we're going to need a drive plate. And it's quite different from the drive plates that we see on the lathe, since it plays two roles. It doesn't only drive the part, but it also fixes it in position. And that's why this drive plate has these set screws. They snug down the drive dog to get rid of any vibration that could hinder the precision of our milling operation. We then have, also mounted on the spindle, this direct indexing plate, and in this case we have one that has 24 divisions. And we have the little plunger that positions the direct indexing plate where we want it. It's important to know that there's two indexing methods, direct and simple, and each one has their own indexing plate. You choose the simplest method that can do the job that you need to do. For us here, we're going to be using the simple indexing plate. So we're going to make very sure that the little plunger for direct indexing is disengaged. On this end of the machine we have obviously the indexing crank, and we can see that when I turn this crank, the spindle rotates. The ratio of rotation between the crank and the spindle is very important. In this case it's 40:1. Almost all the indexing heads have a 40:1 indexing ratio. It does, however, happen, especially on smaller dividing heads, that the ratio is different. Make sure you know the ratio of your dividing head and adjust your calculations accordingly. So that's our indexing crank, and it also incorporates a little indexing plunger that can be inserted into the different holes on the indexing plate. And we can see that the crank turns in both directions, so beware of backlash. After that we have our sector arms and our indexing plate. The indexing plate incorporates a series of bolt hole circles. Now, thanks to Pi, there's only one area where they all line up, and that's where they identify them by the number of holes in each bolt hole circle. Then we have our two sector arms, and they can be positioned and locked in any position around the indexing crank's shaft. The spacing between the sector arms can be adjusted, and we'll see that that's going to help us greatly when we start counting. because we're going to have to count the number of holes for each division that we want to make on the part, and that can become quite confusing. So let's move over to the other side and take a look at the important features on this side of the dividing head. We have in the dividing head a worm and worm gear that have a ratio of 40:1. So that means 40 turns of the indexing crank for 1 turn of the spindle. When I'm using direct indexing, that means that I'm using the direct indexing plate that's directly mounted on the spindle. I don't have to use the worm gear and the 40:1 ratio because I'm moving the spindle manually. And that means that there must be a way to disengage the worm and the worm gear. Well, if I look right here, I can see that I have a lever for that. If I unlock this cam and pivot it, I can turn the spindle manually, or if I re-engage the lever and adjust it, I can use the indexing crank. So that's the worm gear engagement cam. And I also have on this side of the apparatus a lock. It's very important to lock the spindle, mainly when we're using the indexing crank and simple indexing, because when I cut, I don't want the part to be moving around. Remember, there's always going to be a little play in the worm and worm gear, so it's important that when we cut, we lock the spindle each time. Now that we're familiar with the different components of this dividing head, we're going to have to hunker down a little and do some calculating. We're going to have to calculate the movements of the dividing head required for each tooth, and we're also going to have to calculate all the dimensions of the gear we want to cut. So let's head over to the blackboard and do those calculations. Before we start, it's important to say that all the numbers and formulas that we're going to be using here come from the Machinery's Handbook. And this is a good resource to have, but any handbook will do. So, and you don't even need to have a recent copy because spur gears haven't changed in a long, long time. So let's take a look at our gear's call out, or if you prefer, what is the gear that we want to cut? Well, let's take a look. We have 14 dp, 14 teeth, 14.5 degrees pressure angle, and 0.03 of an inch backlash. 14 dp, what does that mean? dp is short for diametral pitch, and diametral pitch is the way that we describe the size of a gear tooth. The size of a gear tooth is determined by its height from root to crest and its thickness. At about its midpoint in height, it's important to say that for two gears to be able to mesh together, they have to have the same dp, or diametral pitch. A 16 diametral pitch won't mesh with a 14 diametral pitch. But there's another crucial thing that you need to know, and that's that even though all the gear teeth of a same dp, so in this case all the 14 dp gear teeth have the same height and thickness, but depending on the number of teeth on the gear that you're cutting, well, the teeth will have a much larger or a much straighter curved side surface. In other words, a 14 diametral pitch gear that has, as in our case, 14 teeth, will have flanks that are very curved. Whereas a 14 diametral pitch gear that has, let's say, 60 teeth, well, the sides of those teeth will be much straighter, even though they have the same thickness and height, because they're all 14 diametral pitch gear teeth. And that's why we have different gear cutters for the same diametral pitch. In our case here, we're cutting 14 teeth, so we're going to require a number 7 14 dp gear cutter. And that number 7 gear cutter for 14 dp is going to give us the curve on the side of the teeth that we need. Now there's more things to say about diametral pitch and gear teeth form, but we're going to leave it at that for now for the diametral pitch, and we're just going to say that when we have a theory video on gears and gear cutting,
well, I'll include all those minute but important details. Let's get back to our call out and look at the next one, which is our 14 teeth. Nothing more needs to be said here. The gear that we want to produce has 14 teeth. That's it. The next one, however, 14.5 degrees pressure angle, well, that needs some explanation. Pressure angle has to do with radial thrust, and that means that when two gears are working together, the driving gear wants to push the driven gear away radially or distance itself from it. Now the shafts that they're on stops that movement, but that can still be a considerable force. If you want gears to be high torque and low RPM gears, well, you're going to be using a very low pressure angle, and that means that there'll be very little thrust actually between the two gears. If, however, you're looking for something that's going to be running at high RPM with low torque, well, those gears are going to have a very high pressure angle. They may want to push away one for the other, but there's almost no torque. The problem with high RPM gears is friction, so that high pressure angle will reduce the amount of friction between the gears. Again, a lot more needs to be said about pressure angles, but we'll get to that in our theory video. For now, let's move on to our final number in the callout, and that's backlash. And we want here 3/1000ths of an inch of backlash. Why do we want backlash? You want backlash because the numbers that we're going to calculate here are maximums. And that means that these numbers represent the biggest that the gear can be. Gears don't work like threads. When we were looking at the threading, we found that we had a maximum pitch diameter and a minimum pitch diameter, and that we could calculate a tolerance for our measurement over the wires based on those max and min numbers. Because of their curved sides, gears don't work that way. The numbers that they give are the largest the gear can be. The amount of play that we're going to have between one gear and another will depend on how much backlash your client wants. Does he want a loose running gear, or does he want a tight gear? One thing's for sure, if you don't include backlash into your gear calculations, you're going to have gears that are so tight that they almost won't be functional. So let's look at our different calculations. First off, 14 dp is an important number, and you'll see that it comes back in a lot of the formulas. The P variable right here, well, that's the diametral pitch. They're represented by P in the machinery's handbook, so that's why I'm using it here. The N that you see here, well, that's the number of teeth. So let's take a look. Our outside diameter, because there's really three things that you need to know to cut a gear, and that is the outside diameter of your blank part, the part that you're going to start with. Next, you're going to want the hole depth, or the height, the total height of one gear tooth. And you're also going to want to know your measurement over the wires, including your backlash allowance. Once you have those three numbers, well, you can cut a gear, as long as you know the number of teeth that you want and that you have the proper numbered cutter. So let's get back to our numbers. Outside diameter of my gear blank. The formula is N plus 2 over P. Number of teeth plus 2. 2 is a constant. It's always going to be 2 for spur gears like this. So N plus 2 divided by P. P is my diametral pitch, and in this case it's 14. So 14 teeth plus 2 divided by 14 equals an outside diameter of 1.1428 inches. Or if you prefer, 1 inch, 142 thousandths, and 8/10,000ths of an inch. Now remember, we're calculating maximums. So this is the largest, absolutely largest blank that you can use. In reality, you're going to want a little smaller than that, and you can easily shave 3, 4, 5 thousandths off of that diameter, and it will still function properly. Just remember that if you touch off your part with your tool to set your height, and that your outside diameter is 5 thousandths too small, well, you're going to have to compensate your depth accordingly. The next number here is the hole depth, or the height of one tooth. And hole depth, the formula is 2.2 inches divided by P, which is our diametral pitch, plus 2 thousandths of an inch. And that's a minimum. And that equals 0.159 thousandths of an inch. Now let's explain. 2.2 is a constant. P is our diametral pitch of 14. And what's this 2 thousandths of an inch? Remember, this is a depth cut, how deep we're going to go with the cutter. If we cut just the 2.2 over P and stop there, those gears will be too tight to function. So the Machinery's Handbook recommends a minimum of 2 thousandths of an inch deeper cut to get just a very, very slight, a few 10 thousandths of an inch of play between those teeth, and produce a gear that's functional, that doesn't bind up. So that's a minimum. It could be a little more than that depending on how loose you want. And we'll see that that is how we're going to adjust our backlash. So 159 thousandths of an inch, that's the depth of cut that we want. But be careful, I am not going to rely on that number specifically to get my final gear tooth depth. What I'm going to do is use my measurement over the wires. So why do I want to calculate this? I want to know the deepest that I can go so that I can figure out how deep I can cut my first pass around my gear and not go too deep. In other words, I use it as a safety buffer. I'm really going to do my first pass somewhere around 130, 135 thousandths of an inch deep. Then I'll measure over the wires, and then I'll do my second pass once I know where I'm going. I've been saying from the start that we're going to measure over the wires. Now if we're going to measure over the wires, and we need two, we're going to have to find out what diameter of wires we need. And the formula for that is right here. 1.728 divided by P, which is our diametral pitch. So 1.728 divided by 14 will give us a wire measurement of 123 thousandths of an inch, or just a couple of thousandths shy of 1/8 of an inch. Now that we know the wire diameter, let's take a look at the measurement over the wires. And that's right here. And our Machinery's Handbook again gives us a chart that gives us a diameter over the wire, or a measurement over the wires, for a 14-tooth gear that has a diametral pitch of 1. So that would be a huge tooth. And that diameter, or constant, it depends how you want to call it, would be 16.3746 inches. Now, our gear doesn't have a diametral pitch of 1. It has a diametral pitch of 14. So all I have to do is divide the diameter that they gave me for a 1 diametral pitch by the diametral pitch of the gear that I want to produce. In this case, it's 14 dp. So this 16.3746 divided by 14 will give us a measurement over the wires for our gear of 1.1696, or 1 inch, 169 thou and 6/10 thousandths of an inch. But remember, what we've just calculated is a maximum. So that's the measurement over the wires for the largest possible gear. We want 3 thousandths of an inch backlash. And our handbook also gives us a chart that indicates to us how many thousandths of an inch less of measurement over the wires I need for each thousandth of an inch backlash that I want. So I want 3 thousandths of an inch backlash, or looseness, between the gear teeth. So I'm going to do 1.169 inches, and that's what I have here. I forgot about the 6/10 thousandths, it's really not that important, minus 3 times. Why 3? Because I want 3 thousandths of an inch of backlash. So 3 times 2.5 thousandths of an inch. And that will give me a corrected for over the wires measurement of 1.162 thousandths of an inch, or 1 inch, 162 thousandths. So those are the numbers that I want my gear to be. But there's something else that I have to calculate if I want to cut that gear. And that's the movement of my indexing crank to get the proper spacing between my gear teeth. So let's erase this and get those new numbers on the board. Now, as we know, our gear is going to have 14 teeth. And the ratio of my indexing head is 40:1. So the formula for figuring out the movement of the indexing crank is 40 over n, or 40 over the number of teeth in my gear. So in this case, it's 40 over 14. But be very careful. You do not want to put that into your calculator and come out with a decimal number. This is one case where using fractions is by far the better choice. And if you don't believe me, try and figure this one out and make the indexing head work with a decimal number. It's just not going to work. Believe me, don't go that way. Use fractions. So let's take a look. So as I said, 40 over 14. Let's simplify this fraction. That becomes 2 12/14. If I simplify even more, that becomes 2 6/7 of an inch. And that is as simple as I can go. But I have a problem here, because the denominator here represents the whole circle number that I want to use on my indexing plate. And I don't have a whole circle of 14 holes. And neither do I have a whole circle of 7 holes. So I'm going to play with this fraction a little more to find a denominator that exists on my indexing plate. And if I bring this up to 21, I multiply the denominator by 3 to get 21, and I multiply my numerator by 3 to get 18, I end up with 2 18/21. Lo and behold, on my indexing plate, I have a 21 hole circle. So this is the fraction I'm going to use. And what this fraction means, written out, is this. I'm going to have to turn the crank 2 full turns, two full turns, and then go on a little further to complete 18 holes on a 21 hole circle. So if I go 2 full turns and then 18 holes on that 21 hole circle, I'll have moved the amplitude required to complete my other cut, and so on and so forth around the part. Since I have a 14 toothed gear, well, I'm going to move the dividing head 13 times, because obviously my first cut, I don't have to move the dividing head to accomplish that one. So there, we have our numbers. So let's get back to the mill and start cutting.
So I have my blank part, and I turned my outside diameter very precisely to the diameter we calculated, rough drilled, and then I reamed it because I want a hole that has a diameter that's very precise. Everything here needs to be concentric. We're going to install this accurate blank on a in-house made milling fixture, and that'll permit us to hold it between centers. So let's install our part. Obviously we're going to have to tighten down very well because we don't want the part to turn on this milling fixture. So we can install the part and the milling fixture between centers. Tighten down, but don't kill it, and lock the footstock spindle. And we can see that we have some play here. Play that we're going to get rid of by snugging up this set screw up against the tenon of the dog that drives the milling fixture. So to get everything snug, we tighten down as much as possible using just our fingers. And then we make certain that there's no play between the tenon and the drive plate, and then we can lock everything in position using this jam nut or lock nut. So now we can start thinking about cutting. As far as the adjustments go for the dividing head itself, since we want to do 2 full turns and 18 holes on a 21 hole circle for each tooth that we're going to cut, we're going to have to find the 21 hole circle on the indexing plate. And there it is. Now, it's a good thing to have found it, but we're going to have to adjust our plunger so that it lines up with this whole circle. Because obviously the plunger has to be able to be inserted into the holes of this 21 hole circle. And as we can see, it's already lined up because I'd already adjusted it. Now I can adjust my sector arms, and I'm going to adjust them to expose the number of holes that I require to do the divisions that I need to do. That way I won't have to count 18 holes for each division, because I'm going to expose 18 holes without counting the hole that the plunger is inserted in. Using the sector arms reduces the chances of making a mistake. So I'm going to insert my plunger in the first hole of the 21 hole circle. I will then rotate my sector arms to come and lean the sector arms up onto the plunger. And then I can check if I have 18 holes exposed, obviously without counting the hole that the pin is inserted into. So 18 holes without counting the one the pin is in, which is already done because I had already positioned the sector arms to the right amplitude. All that's left now before I use the dividing head is to get rid of the backlash, and we'll do that when we start to cut. I can now install my cutter. It's a number 7 spur gear cutter, 14 to 16 teeth, 14.5 degrees pressure angle, so this is the cutter that I need to cut the gear that I want to cut. I'm going to install it on the 1-inch tool holding arbor of this horizontal mill and orient it for climb milling. And now, using a precision square, I'm going to position my tool on the center of the blank. And for that, I'm going to project the side of my blank part vertically using the square. So with the square's blade touching the side of the part and the side of the tool, I'm going to set my readout to 0. Then I'm going to perform the same operation on the other side and divide that number by 2. I'll then move the tool towards the center of the part till I get to that calculated number, and I'll be on center. So I'm touching the blank, I'm touching the tool, I set myself to 0, come over to the other side and adjust so that I'm touching both the blank and the tool. 810 thousandths of an inch, so I'll come back to 405 thousandths of an inch and I'll be on center. Once there, I'll reset my readout to 0. Now that I'm on the center of the blank, I'm going to turn on my spindle, and with the tool rotating, I'm going to come and touch off the top of my part, and that'll be my Z0, the start point of my depth of cut. I've just barely touched the top of my part. I'm going to set my Z axis to 0 here, and then I'm going to back the tool off in the X axis, and that way I'm clear to set the depth for my first cut. I want to cut eventually at a total depth of approximately 159 thousandths of an inch, plus a little more for the required backlash. But for this first depth of cut, since I'm going to want to go once around and then measure over the wires to make sure I get the proper depth, I'm going to go only about 130 thousandths of an inch deep. And there we are. So we can now take our first cut. I'm now ready for our first indexing of the part, and that'll position it for the second cut. So let's go take a look at how to use the indexing crank and the sector arms. I have decided here that to cut this gear, I'm going to be turning the indexing crank in a clockwise motion. So I've taken up the backlash in that direction, and I want to make sure that my sector arms are always leaning up against the indexing pin in a clockwise motion. They have to come up to the pin in that direction, and it's crucial that they be moved for each new cut. So for my second cut, I'm going to unlock the spindle, pull the indexing pin back, and then I'm going to turn 1, 2, and 18/21 of a turn. So I can relock my spindle and I'm ready for my second cut. If you do overshoot your indexing hole, don't just back up to it. Rather, return in a counterclockwise rotation motion 1/2 turn of the crank, and then come back in a clockwise motion to your indexing hole. That'll get rid of any backlash and maintain a constant tooth thickness. I'm now ready for my second movement of the indexing crank. So I want to unlock the spindle, make certain that the sector arms are behind the indexing pin in a clockwise direction, and then I want to count 1, 2, and once again 18/21 of a turn. I can lock the spindle and I'm ready for my third cut. Once I've cut all the teeth and have returned to my original indexing position, I can pull the part from the indexing head and take my first over-the-wires measurement. We're going to need an appropriate measuring tool for our over-the-wires measurement, and in this case we're going to use a 1 to 2 inch standard micrometer. We're also going to need some wires, and I'm going to be using the shank of these 1/8 diameter drills, the shanks being a couple of thousandths of an inch smaller than the business end of the drill. They'll do just fine since they measure 123 thousandths of an inch, and that's what I need. So I can take my measurement by positioning my two wires in opposing grooves, since we have an even number of teeth on this gear, and then measuring over those two wires. Be careful, it has to be accurate. So I can see that my measurement over the wires is 20 thousandths of an inch over what I want as a final measurement. So I will reinstall my part on the machine and take a cut that's half the difference in depth. So since my over the wires measurement was 20 thousandths over what I wanted, I'm going to take a 10 thousandths of an inch depth of cut. I will then re-go around and cut each tooth one last time, and my gear should be complete. But I'm going to make certain before I take it off of the milling fixture that I'm really at my final dimension and that I'm done cutting. Okay, so I've recut all around the part with an extra depth of 10 thousandths of an inch. I'm now ready to remove my gear from the milling fixture and move on to something else because this gear is completed. Gear cutting isn't that complicated, but you do have to be very meticulous with the movements of the indexing crank. So stay concentrated and all should work out just fine. And to everyone, happy machining!